Hey guys, it's Maddie. This is going to be the Unit 7 video overview for the periodic table. And just another disclaimer, just wanted to let anyone know who isn't in our class that I'm not a teacher and I'm not trying to act as one. So let's just get started. So first I'm going to be talking about the introduction to the periodic table. So the history of the periodic table. Johann Dobereiner basically recognized that certain elements exhibit similar properties and arranged those elements into threes or triads. And then Dmitry Mendeleev arranged elements with similar properties by increasing atomic mass, and then by doing so he was able to predict missing elements. And then he stated that there was a connection between atomic mass and the properties of the elements, which, is fair, but really what he was saying was that there was a connection due to the valence electrons, which I'll get to later. Then Henry Moseley came along and arranged elements by increasing atomic number, which is the current periodic table we see today, and provides for the periodic law, which is the periodic repetition of chemical and physical properties of the elements. And then here I have a picture of Henry Moseley, who we credit the current periodic table with today. And then I wanted to go over some terminology that we use when referring to the periodic table. So these columns featured on the periodic table are called groups. And then these horizontal rows are called periods. And then the main group elements are going to be the S block and the P block over here. And the transition elements lay in the D block over here. And the intertransition elements are in the F block over here. Now, transition elements, which I mentioned were the D block elements, their reactivity varies, and they usually form compounds with bright colors. And these intertransition elements have rare chemical reactions and are usually nuclear. Now going over some special names. So we have the alkali metals in the group 1. These are very reactive metals. It's common to see them reacting very strongly with water. And then we have the alkaline earth metals, which are the group 2 metals. They're still reactive, but much less reactive than these group 1 metals. And then we have the halogens, which are the group 17 elements. And they're also highly reactive. And then we have the noble gases, which is group 18. And they're mostly unreactive, which I'll get to in later slides. But then we also have the lanthanides and the actinides down here. And both of them have rare chemical reactions and are usually nuclear. Here I have a graph that I made kind of comparing metals with nonmetals. So the left side of the periodic table usually features the metals. It's most of the elements, around 70%. They're shiny, good conductors of heat and electricity, shapeable, they have a high melting point, solid at room temperature except for mercury, and most have a few loosely bound valence electrons, which is very important to know in chemistry. Then we have the nonmetals, which are referred to as the right side of the periodic table. They're not shiny, poor conductors of heat, pretty much the opposite of metals. They're not shapeable, they have a lower melting point. They're usually solids or gases at room temperature except for bromine, and both mercury and bromine are liquids at room temperature. And these bullets in red letters are very crucial and something to keep in the back of your mind for later on in this presentation. And something to note are that metalloids are usually like the middle ground, so they're okay conductors. Their melting point is neither high nor low. And then here's a little check for understanding. So you should be able to determine which of the following elements are nonmetals. You should be able to describe the general characteristics of metals, nonmetals, and metalloids. And then also be able to name the 2 elements on the periodic table, which are liquids at room temperature. Alright, now we move on to atomic radius. Alright, atomic radius measures the size of an atom. The issue with measuring the size of an atom is that, it's hard to measure how wide said atom is from nucleus to edge of the electron cloud. And this is because the cloud has a fuzzy edge with about a 90% probability of an electron actually being there. So if the surface doesn't actually exist, as the outer surface of a golf ball does, it's hard to actually measure the size of an atom. So to counter this issue, we usually measure half the distance between neighboring nuclei. So you see, these are two atoms, the distance between two nuclei, and then you do half. And that's usually how we find atomic radius. When it comes to atomic radius, we're also able to notice some trends when it comes to, moving down a group or across a period. As you move down a group, atomic radius increases. And as you move across a period, atomic radius decreases. And then it comes to this question, why? And to be able to answer that question, we need to understand two concepts, which include distance from the nucleus and effective nuclear charge. Alright, first I'll be covering distance from the nucleus, which is going to explain why as we go down a group, atomic radius will increase. So as you move down a group, you add an energy level. See, you go from energy level 1, 2, 3, 4, 5, 6, so on and so forth. So you add an energy level with electrons being added to such energy levels that are increasing in size, and I'll show you a visual of what that kind of looks like. So as you can see, as you move up energy levels, it becomes farther and farther away from the nucleus. Greater distance from the nucleus is a weaker attractive force between the nucleus and the valence electrons. You can almost picture it as if paper clips are getting farther and farther away from a magnet. As the magnet becomes closer to that paper clip, there's going to be greater attractive force. But as that magnet moves farther and farther away, there's going to be less attractive force, and the paper clip will be less tightly held. So I mentioned the phrase attractive force, and attractive force can really be explained by this equation. Attractive force is defined by the electromagnetic constant, which is this right here, times the charge of the first and second particles divided by the radius. So as you can see, when radius increases, the denominator will increase, and thus the attractive force as a whole will also decrease. And once attractive force decreases, electrons will begin to pull away from the nucleus and become a bigger atom as a result, since they're not being tightly packed in. The next thing to examine is effective nuclear charge, which is the net positive charge experienced by valence electrons. So as we know, opposites attract. So the nucleus, a positively charged particle, and electrons, a negatively charged particle, will attract each other. However, electrons will repel each other since they have the same charge. So looking at this visual, the electron of interest is the valence electron, and the electrons in between cancel some of the nuclear charge experienced by this positively charged nucleus. So the attraction between this electron and this nucleus is lessened by the electrons in between. However, if there's a stronger nuclear charge, the stronger the attractive force will be. And that's why as we move across a period, the atomic radius will get smaller. Here, represented by the periodic table, you can see each number represents not only the amount of electrons in an atom, but also the protons. So core electrons remain the same, meaning there's not going to be any more electron-to-electron repulsion, but there will be a stronger nuclear charge due to the increased amount of protons. So if charge increases and valence electrons will not be shielded from that attraction due to the non-increasing core electrons, force will get higher because of the protons with a stronger attraction pulling the electrons closer, making for a smaller atom. When it comes to ions compared to neutral atoms, a cation will always be smaller than its neutral atom. Since it's the same element with the same amount of protons, when you lose one electron, there will be less electron-to-electron repulsion, and the charge of the nucleus will become more apparent due to that loss of repulsive force. You can even see that in the sodium atom. Its cation is smaller than its neutral. Anions will always be larger than its neutral atom because it'll have the same amount of protons, but the atom will expand further due to more repulsive force, as an anion has more electron-to-electron repulsion. And you can even see that here with chlorine. Its neutral atom is smaller than its anion. Before we move on to the next topic, I'll have a check for understanding. What is the issue surrounding measuring atomic radius, and how do we counter this issue? Now moving on to ionization energy. Ionization energy is the energy required to ionize an electron, or in other words, the energy required to remove one electron from an atom in the gaseous state. Here you can see an atom in the gaseous state becoming a cation after it loses an electron of energy needed to yank that one electron away. When it comes to ionization energy, the trend in a group is that ionization energy decreases since we invoke distance from the nucleus. Distance increases, lessening attractive force, and the atoms holding onto the electrons are less tight. Trends across a period is that ionization energy increases since there's higher effective nuclear charge. So we need more energy to yank the electron away, thus ionization energy increases. This graph pretty much sums up what I said in the last slide. Ionization energy goes up as you move across a period, and ionization energy lessens as you move down a group, like from helium to lithium. Well, if that's true, why is Al lower than Mg? Well, if you really think about it, when you look at your periodic table, Al is at a higher energy sublevel and farther away from the nucleus compared to Mg. And because it's at a higher energy sublevel, it's easier to yank that electron away and needs less energy to pull that electron away from the nucleus. And then here comes the question, why is S lower than P? Well, if you look at your periodic table, phosphorus and sulfur are in the same energy level, and sulfur is further along. So why does it have lower ionization energy than phosphorus? Well, when you look at their orbital configuration, you have to notice that sulfur has an orbital with multiple electrons. This creates higher electron-to-electron repulsion, and therefore sulfur is easier to remove with lower ionization energy. Now I'm going to be talking about successive ionization energies. So each electron is more difficult to remove than its previous. This is because when you remove an electron, you have less repulsive force, increasing attractive force, making it harder to pull away from the atom, increasing ionization energy. So as you can see, when you try to remove the first electron in lithium, it's much easier to do than the second. And you can also see that in subsequent elements. It becomes harder and harder as you move on to the next electron. And this makes sense because once you have less electrons, there's more attractive force, and then when there's more attractive force, it's harder to pull away and requires more energy. But if you're paying close attention, you can see that the red numbers indicate a large jump in ionization energy. And the red numbers demonstrate the moment core electrons are removed from the atom. Core electrons are generally used to shield the nuclear effective charge that valence electrons experience. But once you start pulling away those core electrons, it becomes increasingly harder to yank successive electrons away, due to the lost protection core electrons otherwise would have provided. Ionic radius and electronegativity. So as we mentioned previously, cations are always smaller and anions are always larger than its neutral atom. In the picture I provided, notice that when we move across a period up until P, the atom's getting smaller and smaller. You can see here to here to here to here, the atom becomes very, very small. For example, when we go from Na plus to Mg2 plus, Mg2 plus is still smaller. Even though they end up with the same number of electrons, you have to keep in mind that Mg has another proton contributing to attractive force. So with the same number of electrons, Mg pulls its electrons in tighter because it has another proton with a positive charge. But then there comes the question, why does this get bigger over here? Why does P3 minus get much bigger when the general trend was to get increasingly smaller? This is because phosphorus doesn't really form 5 plus ions, but instead 3 minus ones. Thus, P3 minus is larger than Si since it has 8 more electrons and 1 more proton, creating greater repulsive force. All in all, moving across a period results in a smaller atomic radius, but that trend is broken when going from cation to anion, and switching from cation to anion means more electrons, which also means greater repulsive force, which would explain why anions are bigger than cations. Electronegativity is the ability of an atom to pull electrons toward it in a chemical bond. The stronger the ability to pull such an electron, the higher the electronegativity. As we move down a group, electronegativity decreases as radius expands and moves farther from the nucleus, making it easier to yank that electron away from the bond. Across a period, electronegativity increases as effective attractive force increases as you move left to right, and that electron is more tightly held in that bond. In looking at this graph, we have to notice that all these zeros in electronegativity are from noble gases, since they don't usually form chemical bonds, which I'll get to later. However, atoms in group 17 have the highest electronegativity, especially fluorine, having the highest electronegativity of all, and I'll get to the exact reasoning behind that, as I said, further in the video. Reactivity and octet rule. So as we've started to see, metals will usually form cations and lose their valence electrons, while nonmetals will usually form anions and gain electrons. Reactivity is dependent on how willing an atom will gain or lose an electron. And just as you can't compare apples and oranges, you cannot compare the reactivity of metals to nonmetals. When it comes to metals, in a group, as you move down a group, the atom becomes more and more reactive. This is because as you add more and more energy levels, metals become more reactive as it's easier to yank electrons away, which is what characterizes the reactivity of metals, how willingly an atom will give up its valence electron. And as you go across a period, the metal will lose its metallic character and will become harder to yank away since attractive charge becomes stronger and stronger as you move across this period, and the goal is to yank that electron away from a metal if it wants to be more reactive. When it comes to nonmetals, as you move down a group, it becomes less and less reactive. This is because it would be harder for the atom to hold on to its valence electrons, which is crucial to its reactivity, as nonmetals become more reactive as it can hold on and attract more electrons. When we move across the period, reactivity goes up since it's easier for that atom to hold on to its electrons or pull new ones in. So we approach this question, why does this all even happen, right? We're noticing metals tend to lose their valence electrons and nonmetals tend to gain their valence electrons when it comes to reactivity. And this is because of the octet rule. Atoms try to achieve the octet, oct meaning 8. Atoms strive for 8 valence electrons, and they want the S&P sublevels of the outermost occupied principal energy level completely filled. And this octet rule helps us understand why there's a tendency for an atom group to form ions of a defined charge. And that's also why we're able to see atoms like nitrogen forming 3- ions due to the fact that they have 5 valence electrons. By adding 3 more electrons, they're able to form 8 valence electrons and be as stable as noble gases. That's exactly why noble gases aren't reactive, since they've already achieved this octet rule.